Okay, so the next problem we're trying to solve is 1443. The question is, the spring shown in figure P1443 has a spring constant of 340 Newton per meter and is compressed to 0.3 meters in the position shown. If released from this position, how far down the slope will block A travel before coming to a stop? Okay, so there's a little picture here. That's a spring, and it is compressed it's in a compressed state. So this is block A. It weighs 4 kgs. Okay. And what else is given? And the mu k is given. Okay, let me write all this information here. So the spring constant K is 340 Newton per meter. The mass is 4 kg. The mass is 4 kilograms. And the amount that it has been compressed, right, is 0.3 meters. And what else is given? The coefficient of friction is 0.8. Okay, these are given. And what do we need to find? How far down the slope will it travel? Okay, so this is in a compressed state. We need to know how far down the slope will it go. Okay, so let me actually redraw this. It doesn't really look like it's in a compressed state right now. So draw it up here. Okay, then maybe not quite, but it's okay. So it's in a compressed state, and the slope is given an angle of 10 degrees. So essentially what we're trying to do here is try to solve this problem based on energy balance, right? So work done by the spring, right? The work done by the spring as it is expanding, or in other words, the work done on the spring while it has been compressed to 0.3. That is, we can get that from the half kx square, the energy in the spring as half kx square. So that energy plus the work done by the block as it moves down the slope, so that means it covers some vertical height as the block moves down, right? So it covers some vertical height, which we can from which we can find the mgh, the potential energy of the block, right? So, and that all is opposed by the frictional work. Frictional work is just the friction times force times displacement. Okay. All right, so let's write this. So the potential energy of the block, I would say, as it moves down, plus the work done by spring is equal to all the frictional work. So this is mgh plus half kx squared equals mu k times the frictional force. Now the frictional force is, if you remember, is the coefficient of friction times force times distance, right? The regular work is the force that moves, force multiplied by the distance the block is moved. But then this force is the reaction force, so I'm going to call this Fn, F sub n, because that's the reaction force. So reaction force times this friction, right? So that's the frictional force times the distance is the frictional work. Okay, so some of the things are already given to us, like m. So m is 4 times 9.81, that's mg, times h, the vertical height that the block track covers, we don't know that yet, plus half, k is 340, the spring constant, and it has been compressed to 0.3 meters, so 0.3 square. So if we know everything from this part of the equation, equals mu k, so that is 0.8 times Fn s. Okay. So here there are two unknowns, h and s, but then h and s are actually related. The height, if we look at this block, right, if we look at the block, this is 10, I'm just drawing an exaggerated view, that's in no world that's going to be 10 degrees, but just so that the free body diagram looks clear. Okay, so if we have done this before, this is our block, right? It's sliding down, so the frictional force is going to be in this direction. Okay, now we have so we have mg acting this way, right? So that is 10 degrees. This also is going to be 10 degrees, so this will be mg cosine 10, right? So this will be mg sine 10 degrees, and then the vertical reaction, the Fn, is going to be like that, and this will be 0.8 times Fn. So I think we have everything, right? So if you look at it, if you think of this as x direction and y direction, along y the only vertical forces are the Fn, which is balanced by the mg cosine 10. So from this we can find Fn. So Fn equals mg cosine 10 degrees. So mg, so 4 times 9.81 times cosine 10 is what? Actually, I'll just write cosine 10 here and then write the answer. So when you multiply all of this, you get 38.64. Okay, 38.64 is Fn. All right. Another thing is, if you look at if the on this slope, if I redraw this slope, let me write Fn here, and this is an important number. We'll be using this back. We got to put everything back into this equation. Okay. Another point is, in this slope, let's say imagine this as a triangle. If the length that the block slides is given by s, and then it has covered a height h, right, and this is given as 10 degrees. So basically what we're saying is, if the block has slid down by a distance s, right, then it has covered a vertical height h, right? That's what we're saying here, mgh. Okay, and we have s here. Then this h and s are related by our simple trigonometry, right? So we can say h is equal to s times sine 10 degrees. So h can be replaced by s sine 10 degrees. Okay, so this is another, oops, didn't mean to do that. That's what I meant to do. Okay. Right. So these two equations that I have, these two things that I have highlighted need to go back into this, the first equation. So we get 4 times 9.81 times s sine 10, 4 times 9.81 times s sine 10 degrees plus this is 170 times 0.3 square. So let's see what that comes to. 170 times 0.3 square is 15.3 is equal to here 0.8 times Fn is 38.64. 0.8 times 38.64 times s. Okay, so 0.8 times 38.64 is 30.91. So it's basically this is equal to 30.91 s 15.3 plus what is this, 4 times 9.81 times sine 10 degrees is 6.813814 s. Okay, and this is 30. This is okay. So all of this, when you put all of this together, let's see what you get. The value of s, we have s here, s here. So you get s is equal to roughly 0.635 meters, right? along the slope.